Hi, welcome to Functional Just in video 4. I've been working mostly in Scala for about 6 years, and I'm a long-time advocate and practitioner of pure functional programming, and I started making these videos for fun, so I'm glad some people started watching them. So this series of videos, if you just find it now, will be released every 1 or 2 weeks, and I cover topics around the Scala programming language and also pure functional programming. If you do enjoy these videos, please like and subscribe, tell your friends and work colleagues. So in episode 1, I developed a expression evaluator in Scala and used some of the new Scala 3 features like context functions and the significant white space and the new implicit syntax. In this video we're going to go back and look at that program. We're going to be adding error handling to it using the either data type. And in order to do that, we're also going to talk about pure functional programming, and we're going to implement our own Functor type class from scratch. And we're also going to make an instance of the type class that works for all eithers, and that will take us into the new Scala 3 type lambda feature. Alright, so let's start by looking into the code that we did in the first week, and first we'll do a recap of how that expression evaluator works. We have a algebraic data type called exp for expression, and that gives us different kinds of expressions that we can evaluate. So we have value, which is going to represent just numbers, integers. We have add, which can add two expressions together. We have mul, which can multiply two expressions together. And then we have var, which takes an identifier and looks something up in a symbol table. So then we have a type called env, which is essentially our symbol table, which is just a map of strings to ints. So between these things we can write expressions that are sort of like an expression tree. We can call a val on them, and we can calculate the value of the expression. So here's an example of an expression, and I've laid it out like an actual tree. So in this case it's adding the variable z to the sum of the raw value 10 and multiplying these two variables x and y. So then when we call this, we give it an environment, which is a symbol table using the given keyword, and then we call a val, and then we'll get the result. So we can run these, and we should see it compile and run, and then we get the results of the expressions. So first of all, the big problem with this code is this, where we do get on an option. So in this part of the code, I just want to recap what with env is, the return type of all of these expressions. So what that syntax means is we have a function which returns the type int, and it also has an implicit type env, and all of the functions in a val and all of the subfunctions that it calls all have the type with env. So that means any one of these must have an implicit env type, and then when we need to use it, we use the summon keyword. So most of these functions don't need the symbol table, only the handle var code does, and so that summons the environment, gets the symbol table, and then we can call get on that to get the symbol. Now the get function actually returns an option, so then we have to call get on the option to get an actual integer, so that we can match the return type. So this code works as long as the symbols exist, but we'd like to make it more robust than that. So you should never see this pattern in serious code, in production code. So at the very worst, you would do something like get or else, and call the symbol and then provide a default value. Right, so this code will still work if, for example, we called a symbol that didn't exist. So if we had a symbol a in one of our expressions, and symbol a is not in the symbol table, when we call our code it still works, but obviously it might not be ideal that you're just sticking zeros in your code wherever, so we might need a more principled way to handle it, and in fact we will need a more principled way to handle it. So what we'll do is we'll put this back to how it was. In fact, we can leave it that way for now, it's fine. But another thing we might want to do is, instead of having a return type of integer from our expression evaluator, we could use either instead. we'll just say string is the error type and int is the result. Alright, so if you save that, you can see that most of the code works. We've just got some errors to fix. So we can change this to right, which just means that instead of raw values of type int, we're just going to return right. Okay. Now these ones are a bit more complicated because we need a way to add and multiply ithers, and obviously we don't have any way to do that. And that's kind of what we're going to lead up to over the next couple of videos. So how do you convince Scala that it can add and multiply ethers? We really want to have it adding and multiplying numerics. So it's going to be a little winding trail, but the first thing we've got to get into is what pure functions are. So we want our expression evaluator to be a pure function, and pure functions have several properties. In fact, pure functions are, you can think of it as just a way to map values of one type to another type. Let's see an example function. So say we have an example of a function that just takes an a and returns a b. Let's just provide those as type parameters, and then it has some implementation. Alright, so to be a pure function, this function has to be total. That means that every a that we can input to this function returns a b. And that's a one-way relationship, right? So we don't have to map every b, but we do have to have every single value of a must return a b, right? And it mustn't return anything else, so it can't return an error. So if our program, for example, if we let's just go back to how we had it. So our bad version of the program will emit errors. If we run this now, you'll find that it will throw an exception and break the program. Right, so that's not a pure function. So we can't throw errors. It must be deterministic. Which means that every a returns the same b every time. Okay, so you can call the same function over and over again and you'll always get the same result. And the third thing is no side effects. So you can think of errors as being side effects, for example, because other things that are side effects are printing to the screen, reading a database, sending a web request down the wire. All those kind of things are side effects. But also things like errors are side effects. And the way we deal with side effects in pure functional programming is with data types and type classes that can manipulate those data types. So, for example, the Functor data type, which you'll find in Haskell and Scala. Functor gives us a way to map values that are not just simple types like a and b, then they have some kind of special embellishment, right? So in the case of the either type, we can represent a value that has success and failure. So let's say we had a either string int. This could be a successful value like a 10, or it could be a failure value like oops. So with the same data type, we can represent a computation that returned a value, or it failed and it has some kind of error. And there's lots of high kind of types like this that can represent effects. So some other effects are option, which is representing the effect that something might be missing. We have lists, which represent the something being in multiple states at once. And then we have things like the IO data type or future, which represent or usually represent actual side effects like printing to the screen or doing some kind of file operation, and they encapsulate them. And in all these cases, we have different data types to represent different things, and then we have type classes to actually utilize them. So for example, in our program, we're later going to need to add numbers to eithers. So if I wanted to say add 1 to e1, then what I need to do is use the Functor map function, and that's going to take the value of e1 if it succeeds and add 1 to it. So let's call that e3. And what did we get there? We got an either string int, because when you map something, it doesn't change the data type. What it does is applies the function to it, but only if it's a success, right? So our pure function here is only concerned with adding numbers together. And if we were to run this and see the result, then you'll see that the program has no problem adding 1 to the number, even though it's in an either. Let's make a failure case. We want to add 1 to e2, and when we run this one, we don't get any errors or exceptions. We just get oops, right? Because if you try and run a function on a value that has an error, then you just get that error back. So going into functors in a bit more detail, a functor in Haskell and Scala is just providing you with the map function. And the reason I came to the Haskell page is that it also details the functor laws. So these laws are there to say that if you implement a functor, then it must also obey these laws, right? So in Scala, functors don't always obey the laws, right? So they will with things like either and option and list, but when it comes to things like future, they might not. So what we're going to do is define our own functor, and then whenever you see that we've explicitly used a functor, then you can guarantee that it's actually using the laws. And also it's a fun exercise. So how do we implement our own functor? Well, let's get rid of this, and luckily some of the work has been done for us. We can go to the Scala documentation, and we can see here that it's quite straightforward to implement functor. We're going to implement it as a trait, just like we did with the numeric type class in a previous video. And we're going to take this version of it, which implements map as an extension method. And what I'm going to do is just rename this fmap, because I want to be able to make sure that we're calling the right one. Alright, so let's say what I wanted to do was to run our function again. So we're going to take the E1, and now we're going to fmap it with a function that adds 1 to it. Alright, so we can't do that yet because we've implemented the functor definition, but we haven't implemented it yet. We don't have any instances of it. So what we need to do is implement an instance of either for our new functor. So fmap is in red because we don't yet have an implementation of fmap for lists. Sorry, for either. So we're going to provide that implementation now. So first thing we want to do is define a type. So we're going to make a type called a string either, and this takes the parameter a, and it's going to be using string as its error type and a as its success type. And then we're going to provide a given instance for that. So this will be a functor that works on string eithers. And then we're going to let's do the new syntax, no braces. And then we're going to provide the extension method that we need. And then we need to replace the wildcard type with this type. And then we got to provide an implementation of this. So essentially this is going to be we're going to have to match on X, and if we get a right value type A, then what we want to return is a new right value which provides FA. And if we get a failure, so some kind of error, then we need to package that up in a new error. Alright, so that's the implementation of string either. Now we can run that. And let me just print out the results too, just for sanity's sake. And what you should see is that it incremented the first one and then the second one failed. So that's actually pretty good start. So now we can implement functors for eithers. Now in our program, we're not going to use strings for the eithers. We're going to define a algebraic data type for the errors. And so for that purpose, we'll have to make another functor, right? So we can't just copy and paste this one. We'd have to make our own. So obviously that's not ideal. What we need to do instead is look into a new feature in Scala 3 called type lambdas. Now Scala 2 had type lambdas too, but the syntax for them in Scala 3 is greatly improved. But what that will let us do is create a functor for an instance of not just string either, but any kind of error type on the left, right? So we'll just comment this out. Now we're back to where we were. But what we're going to do is just implement a generic version of the same thing. So what we're going to do is use the given keyword. This time we're going to actually name the functor instead of in this one you can see that it's anonymous, doesn't have a name. In this one we're going to actually name it, and it's better practice to name them even though you can leave the name out, especially in libraries, because it just makes the code easy to work with. Then we're going to provide an instance of functor. Now this is where the type lambda comes in. So what we're saying is we want to specialize this functor for things that have a type parameter e, which represents the errors, and then it's going to look like this. So we have an e and then an a. Sorry, this is wrong. This should be a. So the type parameter is a, and then we have a type parameter here which is sort of higher up. So this would be an EA, and that's how we define the functor. And sorry, I've used the wrong symbol, it should be this one. And then we need to copy the actual code. So uncomment that. Alright, so now what we can do is right here, instead of using string either, we can just say this is actually an either EA, and this is an either EB, and boom. So this syntax is a little bit jarring. The syntax in Scala 2 was actually way worse, but if you can just look up examples, there'll be a blog post for this one, you can copy and paste it. Essentially it's a lot nicer than it used to be. So that gave us a way to make a generic functor for any kind of either. Alright, so let's say this either had a different error type. say an integer error type, and instead of returning a string, it's going to return the error 10. And now we can run it. There, and now you can see that it returned a different type. So what we've done here is introduce Functor, demonstrated why you need it, and created a generic instance of either Functor that works for error types that can be polymorphic at compile time. And that's pretty cool. So the next step here is we're going to also need to look at monads. So we'll implement monads. Once we have Functor and monad, we can go back to this expression evaluator and rewrite that so that it returns either numerics, and then we'll be able to make a much more generic version of it with error handling. So if you made it this far, thanks for watching. There's going to be links to the blog post and to the code in the description below. So if you like the series, please like it, subscribe, tell your friends, and thanks very much.